Good afternoon, tēnā koutou katoa. Welcome to our second EEA winter webinar. For those of you who don't know me, my name's Peter Berry and I'm Chief Executive of the Electricity Engineers Association. This is a very special time. As you know, we made the tough decision to cancel the EEA conference, but never say die. We do have bits of it being revived through these winter webinars. It's the first time we've cancelled the conference since World War II. So you can understand the impact that COVID is having on the world when we cancel our conference in 2020. However, given the collaborative nature of the EEA, the high number and quality of abstracts offered for the conference and the EEA's desire to offer new ways of engaging with members, the EEA Asset Management Group agreed to host a series of technical webinars. We partnered with the Epicentre at the University of Canterbury to provide an opportunity for our future engineers to engage early with industry on the many issues that we're challenged by at the moment. Over the coming months, we'll also bring in other technical experts to partner us in these presentations. So, it's new for the EEA. This is webinar number 2. We have our technology trainer wheels on. They didn't all fall off for the first one, but we had a few speed wobbles, but we are getting better. So remember when you're doing your presentations or listening to make sure that your mute is off, and also be kind today. It is Tuesday and it's never a good day of the week. So be kind and enjoy the presentations coming shortly. The theme of the EEA conference was engineering, technology and innovation in a low carbon environment. So we're building the webinar series around the key issues that relate to this theme. Today we're looking at emerging technology uptake, new technology that's allowing us to monitor more asset information, obtain information quicker and simpler than we could ever have imagined. Today we have 3 organisations talking about what they are doing with new technology. The New Zealand Productivity Commission report on technology adoption raised a couple of key issues. That technology adoption by individual companies and firms will improve productivity directly. And secondly, experimentation is fundamental to innovation. Policies that are overly prescriptive about business models, technologies and market boundaries or impose high exit costs on firms can discourage experimentation and hence innovation. From the 3 speakers today, you will hear how preparing and implementing emerging technology has assisted their organisations to improve and the impact that technologies have had on the grid and on managing future maintenance. It's fantastic that the 3 presenters you are going to hear from today are all progressing, planning for the future with its many unknowns with their organisations. The snowball of technology has left the top of the mountain, so let's get ready for what will be a challenging and interesting ride for our industry and our engineers. As I said, this is the second of the 4 planned webinars. Please enjoy the presentations. Take the learnings and insights from the presenters' topics. It's now my pleasure to introduce the moderator for today, who's Roger Griffiths. Roger is General Manager, Assets and Engineering at Westpower, and he's also a member of our Asset Management Group. So I'll get Roger to introduce each of the presenters in turn, and it's now my pleasure to hand over to Roger. Roger, over to you.
Thank you very much, Peter, for that fine introduction. We've got an exciting lineup of speakers this afternoon. So without further ado, we'll move into the highlight of our afternoon. Our first speaker is Nutman Rashid from Unison, and the title of his talk is Enhancing Rating Studies Through Soil Digital Twin. Now, Nutman Rashid is a digital engineering specialist in networks, or in the Networks and Operations Division at Unison Networks Limited, New Zealand. Nutman presently leads the data-driven decision-making workstream within the company's digital strategy. Nutman holds a PhD in electrical engineering from the University of Canterbury and is currently expanding his knowledge and passion in the data science field. Electricity distribution network planning and design relies on good knowledge of field conditions. For underground cables, knowledge of the soil conditions allows network operators to optimize the selection of their asset to operate in the identified environmental conditions, whilst ensuring it has enough capacity to meet the local demand. The technical challenge is to streamline the process of data collection from thermal sensors, soil samples, local site knowledge, and then using those data to infer the exposure of distribution assets to the varying environmental conditions. With the availability of sensors, improved cellular network, and increased application of the Internet of Things, it presents an opportunity for network operators to digitalize spatial data from the fields and turn it into actionable information. So without further ado now, let's hand over to Nutman and he can deliver his presentation for us.
Thank you, Roger, for the introduction. And I would also like to thank EEA for organizing this series of webinar. I think it's a good opportunity for us as a company to discuss and present what we've been doing to the rest of the industry. So just to check, can you hear me okay? And can you see my slides? Awesome. Okay, so today the topic of my presentation is on enhancing rating studies through the use of soil digital twin. So I'm Numan and I'm from Unison. So today this is the overview of my presentation. So I'll start off with the background of why we're doing the soil digital twin, and then I'll walk through the different steps that we've done to achieve this particular twin. And I'll finish off with the conclusion. So what we're seeing as a technical challenge is that we carry out different projects in the field. Throughout the different project, we collect different data, but how do we actually streamline the different process and use that data to identify thermal stress on our electrical distribution asset? So for a particular piece of project, we may perform a study on a particular site, gather as much info as we can on the soil condition so that we can optimize the use of our underground cable. So in the past, or existingly as well, people may have an avalanche of paper-based form that you can't really look at it into detail. So what we were trying to do is try and digitalize this into digital form to then perform rating studies. So as we know, underground cables are exposed to different environmental conditions, different heating from being underground, and to get a good optimization of the capacity, we need to have a good knowledge of the field conditions. So we can perform different things to perform rating studies. So we can use static value, which is the one labeled in red. We can use seasonal rating, having summer winter value. We can also perform real-time monitoring on the field to collect soil temperature, for example, so that then we can identify what capacity we can apply to the cables based on known field conditions. So today, as I mentioned, my talk is about the soil digital twin. So this is an overview of how we achieve the soil digital twin. So it comprises a series of input and process that input to then develop an output which can be used throughout the business through ArcGIS. So here so the key items that we have 4 key items. So firstly, we have the field data. So we try and collect as much field data as we can so that we can then process that data to perform some analytics. So when we go out to site, for example, we collect some soil sample, which we can then perform soil studies at our soil lab. So what we've done is we've have a web form or a form that basically a tester can key in and generate a thermal dryout curve, which we can then use for carbureting studies. So we collect three different set of properties. The three key main one is the soil emulsivity, the moisture content, and finally the type of soil. Next, what we also done is that we gather data from the field itself, on-site data or in situ data from right at the cable. So what we've done is we inserted probe within 5 centimeter to the depth of the cable, as seen on the figure on the right here. So we inserted several probe, maybe 1 or 2 if there's several cable in the vicinity. So we capture those data into the logger and send it back to site. So we use Pi as our historian at Unison. Next, what we do is we look at any publicly available data that we have. So it can be from government bodies, in this case from GNS Science, maybe some research institution, and also we also have council data from Hastings or regional council. So what we're trying to do is essentially gather as much data as we can, so that we can, develop some knowledge on our field conditions. Once we have this field data, we start to pre-process them, tidy up any anomalies. If there's out of range data or data that doesn't make sense, we pre-process this and collect the field data so that we can perform further analysis and processing. Once the data has been cleaned up, we process them and import it into ArcGIS, which is basically our repository where we perform our soil digital twin. So in terms of the technique that we use to achieve soil digital twin, there are several techniques. So the technique in GIS is called spatial interpolation. So based on some known points that you know from the field, you interpolate it to the other unknown points. So there are several different techniques that we can use. So the figure on the right here, an extract of a chapter from Wiley on spatial interpolation. So you have, so there's 6 here, but there are more. So the method that we actually use is the inverse distance weighting. So I'm not going to discuss in detail what are the different options, but what we've done is we perform some validation in terms of which method would be best suited for our soil digital twin. What we found was that inverse distance weighting, or IDW, provide the best performance if we have limited data, for example, and so that's the reason why we've chosen IDW, or inverse distance weighting. So the underlying data itself, we have a mix of historical, daily, and regional value based on the input that we gathered from the field. By having this, it allows us to generate different map based on different time period. So for example, the figure on the left, bottom left, that's the soil map generated based on winter data. And the one on the right is based on summer data. So the figure looks a bit coarse, but that's purely because it's zoomed out. So if I were to zoom in a particular spot, so you can see that the inverse distance weighting allows us to get some contour of the thermal resistivity from the known points or the measured points, and interpolated that to the unknown region. So with this set of information and properties, essentially give us some digital readings of unknown points, which is, so for example, in the middle here, we have, I've clicked a particular point on the map, which gives us the latitude and longitude, and it gives us the thermal resistivity value of that particular location. So essentially, each lat and long, latitude and longitude, will have its own interpolated thermal resistivity values. It will have its own interpolated temperature. It will also have some land cover value based on if there's any available council data, for example. So essentially, it's a rich map of containing all the different data that we have collected. With the interpolated thermosivity and temperature, we can then use that information to perform rating studies. So the figure on the bottom right is basically a SIMCAP, which is the tool that we use for rating studies. So two of the key parameters required for that particular piece of software is the soil temperature as well as the soil thermosivity. So using this, we can estimate what's the likely condition is at a particular location on the map. So to conclude my presentation, so essentially the digital twin provide new opportunities for us to do rating studies. We can tap into a wealth of field data at a central location. In our case, we use ArcGIS. Using true soil spatial interpolation, we can infer properties using the soil digital twin at unknown points. And at the unknown point, we can use that predicted value and the interpreted value for our rating tools in our rating tools using SIMCAP in our case. Additionally, when we carry out other projects, we can gather more data, which we can feed back into the repository or data set to then refresh the data for different time period. Additionally, if we were to do other project, not underground cable, we can actually overlay other assets as well as a layer. This then allows us to provide a better judgment of our projects in the field. So that's the end of my presentation. Thank you for listening and participating.
Thank you very, very much for that, Nutman. That's incredibly interesting. I didn't even know we had those sorts of skills within the industry. Now, I haven't seen any questions coming through on the Q&A board, so I'd encourage everyone, you must be burning with questions out there. Please feel free to type some in, but until then, we've got a few minutes, so I had some questions for you, Nutman, just to keep you on the ball here and see if you can help us out. You mentioned there you had your own soil lab in Unison. Could you tell us a little bit about the equipment and the personnel and some of the work you do in that soil lab?
So I didn't discuss the lab in detail. So if you have a look at the, can you add? Yep, am I back? Yep. Sorry.
Yep.
So the figure on the right here. So I've labeled the different equipment that we have. So essentially, what we have is right at the bottom there, just some soil sample that we may have gathered from the field. So that soil will basically goes into a tube, which the soil will then be heated up to provide this thermal dryout curve. So the thermal dryout curve essentially tells the engineers what are the likely in situ condition for a particular site, and it also provides us a range of the likely thermal resistivity that the soil will experience. So the axis on the bottom is moisture content. So if you have a very dry soil, you will have a very high thermal resistivity. The more moisture content you have, the cooler the condition of the soil, then you would expect a lower thermal resistivity, which is actually beneficial to the cable rating.
Cool. That's really interesting. And what's your so that device on the right there? That's the oven for heating the sample.
Yes. So because being in the lab, what we try to do is we first we dry out the soil. So we have a zero moisture content. So slowly we increase the moisture by adding water. So so as you add water, we use the probe to measure the thermal resistivity and we keep going until the soil cannot retain as much, cannot retain the moisture anymore. So that it start to become sludgy. So that's essentially when we stop adding moisture. I mean, we have a range that we deal with anyway. So essentially from 0 to 33 tends to be the maximum.
Okay, understand. Thank you for explaining that. So this is quite a specialised setup here. Do you provide those services to other EDBs around the country, for instance? Is that something you do, or is it just for internally for Unison?
So this particular is the work kicked off during the smart grid phase.
Yep.
So in the past, we used to approach consultant to provide this kind of study. But what we found was that the moisture content and info that they provide tends to be limited. So sometimes they only provide 3 moisture content, which is sometimes not enough for us. So we approach someone from Geotherm, or like someone from Canada, which is like a soil, I guess you can say he's a soil guru. So he helped us set up the lab. So I guess to answer your question, currently it's only for our sort of purpose.
Okay, I'm sure it won't stay that way for too long, Nutman, once everyone realises the the tools that you have available there. Well, look, that's been incredibly interesting, and I really like the way that you used remote sensors, the inverse distance weighting. I must find out how that works from you more to give yourself a contour for what's happening with your temperatures and with your thermal resistivity. So applying all that onto a GIS layer, I guess that then gives you the ability to look at any particular cables in your network, look at what their ratings are, with a dynamic rating, and then look at what the currents are to determine how hard you're running the assets. Is that how you do it?
Correct. That's exactly it.
That's perfect. I'm sure Mercury would have loved this sort of technology back in about 2005. It could have come in really useful and averted a few disasters, couldn't it? Well, thank you very, very much, Nutman, for presenting that to us. Very exciting, well done, and thank you for coming along to share that with us in our webinar this afternoon.
Thank you.
Well, we'll move along now to our next presenter. I'd like to shortly introduce Darren Lusinski from Electra. So the title of his presentation is IoT for a Smarter Grid. Now, Darren has spent his career leading technology development and implementation teams for several commercial entities. Many of his developments and designs lead to patent filings with IPONS and the World Intellectual Property Organization. Darren has a patent in battery management and is chair of the New Zealand Electricity Networks IoT Forum. Low-cost Internet of Things is, we call that IoT, is enabling LV network monitoring and customer participation in a transactive grid. Together with providing low-cost visibility and control for parts of the network not previously monitored, it also facilitates low-cost, real-time interactions with consumers, providing them with real-time energy management choices. The realisation path at Electra has implemented IoT comms media and progressively connected devices with desired capability across all voltage levels, including LV. It sounds incredibly exciting, doesn't it? So let's pay careful attention now to Darren as he presents this to us. Darren, I think you might still be muted.
Is that better?
Much better, thank you.
All right, so you can see my presentation?
We can indeed. Excellent,
okay. So, well, just a quick rundown. So Electra is based in Horowhenua and the Kapiti districts, and we split into a northern and southern network. We've got about 45,000 customers, 2,500 transformers. And we have a SAIDI limit of 83 minutes, which will appear. I'll make that connection later. Myself, I'm an electrical engineer with a development background, and I'm used to agile projects with some multiple unknowns. And Max was the GM of a lines business at Electra when the project was the inception in 2018, and he developed the overall plan and strategy that ran the project. So moving on. So just the topics we're going to go through was just why did we even do this in the first place? Where was our project vision and strategy and goals around this? We had some questions about IoT that we wanted to work out quite quickly. We knew that there was a variety of IoT communication options, and we wanted to investigate those. We selected LoRaWAN in the end, and I'll come to why we did that. We then developed a bunch of IoT project streams, and they were based on things that we thought we could get the most benefit from. And I'll go through sort of the description of those projects and what we learned as we went. Then what we're going to look at next, what we learned in operational experience and implementation experience, and then the overall learnings from the journey. And then a little bit of a blurb about our IoT forum that we run that enables us to share those learnings. So why do we do it? Well, Electra has a group strategic plan, and we were very interested in developing a new and investing in the future. And we wanted to become more knowledgeable about IoT. It's a wide topic. We wanted to we define it as a comms platform, but what are we actually going to use it for? And then we knew it was economical, but and certainly the telecos told us that it's low cost, but actually how low is it? And we needed to investigate what that meant. And then the issues between having a public or a private IoT network. So we knew the public networks, LoRa, Cat-M1, NB-IoT were all available by the telecos. Sigfox is available, even satellite. But if we were going to go to a private one, which one could we pick? So there are a few questions around that. And then we also wanted to gain some implementation experience. We wanted to set some stuff up, set up a platform, see how all that data worked, develop some sensors, and then find out sort of really how it all works. And one of the things we did discover is a bit of a spoiler, is that installation cost dominates just about everything. So moving on, our project vision, strategy and goals. So clearly more data gives us better decisions, and we're always wanting to improve our operational performance all the time. So operational maturity is something we strive to achieve. The international trends where that more PV, more DR is getting out there because lower battery costs. Transaction of energy market is in New Zealand and starting to appear. So we wanted to have a little bit of experience with that. Also our customers, we're also keen to reduce their energy costs, automate systems, try and push notifications out to them and see what sort of remote interface we can provide to them. In the past, we don't generally, as a lines business, talk with customers. We sort of seem to have lost that connection. And then as a strategy, we really had little LV network information. That last mile is surprisingly the largest loss, and we didn't really know a great deal of what was going on. I wouldn't say we didn't know anything, but we certainly wanted to know more. And to monitor in the past, previous comms was just so expensive, and clearly IoT is a cheaper option presented itself as a nice option for us. And certainly other ELBs are looking into the technology worldwide, and we needed to make a start. And even if that answer turned out to be that it's not for us, we still needed to have a look. We have a commitment to looking at new technology. And then we wanted to see what data visualization and backend interface we would have to develop to be able to seal this, so alarms, status data, and could we use it for possible load management? So certainly something we're interested in doing. And then can we expand that into customer energy management, more push notifications, and certainly the if this then that technology's around. So we wanted to see if we could leverage on that for our customers as well. And certainly a goal was to develop an IoT network, and you know, we needed to build and deploy, test and refine, and really get a little bit better at what IoT meant for us. And we really wanted to focus on LV monitoring. That we felt to have the greatest benefit, and it was the area where we had the least real-time knowledge. And then we were interested to see what service we could push out to our customers. So electric vehicle, load management, DER, those sorts of things. Can we do that? And clearly, with load management, we get lower costs, we improve efficiency. So we then sort of discovered we had it led to a whole bunch more of questions, and certainly, you know, what is IoT? Well, for us, IoT meant low-cost communications. That's how we envisage it. And you know, is cents per year real? And certainly we've got some devices out there that cost us 8 cents per annum to operate. So very, very nice. Is it long range? Yes, we've been trying to work out exactly what the ranges are and how it works, and we've got some good results there. But it is slow. It's certainly slow for two-way communications, and we're seeing sort of a polling response around about 4 seconds. There's several IoT platforms out there, so which one was it? You know, we looked at Sigfox. It's comparatively expensive and a very small payload, only 12 bytes. We looked at the narrowband IoT and Cat-M1 and their teleco options, but they're still in testing really. Even though they've been here since about 2017, they still seem to have not really taken off very well. And it's based on cellular coverage. So even the pricing was close to what we've seen before, GPS. And then what sort of back-end support and costs were they going to incur? And we certainly knew that IoT, NB-IoT was big in Europe. There's millions of connections, but you know, Vodafone it's new to New Zealand, so we hadn't seen any real deployment of any tools using NB-IoT. And then, you know, LoRaWAN for us really turned out to be a good option. It was one of those things where we wanted to see what could we implement quickly, and certainly LoRaWAN seemed to be something we could get into quickly. And then, you know, certainly more platforms will appear, but then, you know, was there any real benefit in waiting? We've seen the ones that we've got. Maybe we should just get going, and that was the general expectation. We wanted to see who else was working in this space. Unfortunately, not too many developers in New Zealand. There's a lot more in Australia. We've had a few developers in New Zealand, but they've got virtual products, and they're more wanting funding. They actually haven't got something hard to put on the table and show us. So that didn't really get us very far. And then certainly the operating expenses were high in some of these options. So that sort of really threw out the window the low cost IoT concept. So that didn't work so well for us. And then we wanted to then create our own IoT forum and really start to share the knowledge that we had developed looking into these things. So we formed an IoT forum amongst the Lines boards, and we've had some success there, and we've met and we've shared details, and it's worked very well. And then, can we leverage IoT? Can we rely on this data? Unfortunately, it's low power and it's not always effective for communicating. So we needed to look at putting gateways where we had we don't have cost-effective options right now, and where we don't have any coverage. Certainly, we didn't have cellular coverage, perhaps, but we knew we could put in a fairly cheap gateway. And we needed to work out where to put those gateways, what sort of range, what sets of location, what do they cost, how many do we need, and then what are the OPEX and CAPEX commitments of putting that in. And We then went on to a few more, and it was, can we even make low-cost sensors? And digital sensors, yes, mostly. Analog tends to be a little bit complex, but it's the sensor part that really dominates that cost. And then anything we did make, we were very concerned about safety and compliance, and especially with the analog, because they are actually measuring something and actually touching things. So that was of concern. So we wanted to try and stay standardized. And then how do we get the data back? We had a vast array of server options. We wanted to pick something that was going to be of low cost at the beginning and maybe had an open license, and we found one. We needed to find out what features that it needed, and this MQTT we discovered earlier was something that it needed, and that stands for Message Queuing Telemetry Transport, and it's all about data distribution using low bandwidth comms and slow. And it's not new, it's been around for a long time. It was sort of based on paging technology. And certainly we knew we could push this data back into SCADA, and SCADA's fairly easy, but we had an advanced distribution management system. We wanted to try and put it in there and see what we could do about pushing it out to our outage system. And then all of this stuff created lots and lots of data, and then what did we do with it? So we ended up having to look at creating a data lake to store all this data. And then how quickly did we get that information? What was the latency? And we certainly noted that satellite latency was in the order of up to 2 hours, and that certainly wasn't useful for fault identification and those sorts of things. And then where do we start? So again, we got into developing some use cases, and it was really about what items could we develop that had low data volume and only used tens of bytes or maybe hundreds of bytes. Certainly digital turned out to be the easiest, so status monitoring type activity, and it has the best battery lifespan of up to 10 years. However, we found analog to be costly. There was more data plus the interface, and it usually needed to be powered by the mains because it needed constant monitoring, and certainly a different animal to a digital one. And then how long would it be before we could do anything? So that was all about choosing some solutions that had the highest benefit, were low in effort, cost and development time, had minimal field testing requirement, were easy to install and deploy, and if we liked it, it would scale well. So these are all concepts we were floating around with, trying to come to a conclusion. And then, you know, what did this cost? And we discovered gateways sort of around about the $4,000 mark, so around about a little under $5,000 installed. IoT server to actually capture all that data. Options there, what was available. You can get free versions, fine. Bespoke IT service systems were very costly, and we didn't really know what we wanted, so we weren't keen to go down that path either. So we just thought, let's just start moving. So the first thing we came up with quite early was, well, what are we going to call an IoT sensor? And we thought, all right, first off, we don't want to try and reinvent the wheel here. And so sensors, we decided sensors should be as standard as we could possibly get them. And this was mainly so that we could effectively grab them off the shelf. If they failed, we could get warranty replacements. And it wasn't a case of we had a bunch of orphans sitting on a shelf that once that person who developed that item in the company left, nobody knew anything about it. Back-end integration we already knew about. We already had all of those things in place. So really the IoT communications was the real component that we needed to try and work out, and it needed to be something that we could swap in and out, so that we could not necessarily use LoRaWAN. If we wanted to go to radio or microwave or cellular or any of the other technologies, we could without having to do dramatic changes to the actual device design. So it was something that we decided that sensor was standard. Back end we already had, it was that IoT communications, what's the best option for us? And when you look at the option, the sort of the spectrum of IoT communication options that are available, You can see there that LoRaWAN sort of sits in the low cost area. It's got fairly good range. It's got low data rate though, but certainly in terms of all of the other technologies around there, it's the best bang for your buck. Certainly as any of the data rates go up, so does the costs. So LoRaWAN, based on that criteria, worked well. And when we really drilled down into the technologies, we found that LoRaWAN really ticked a lot of the boxes for us. And the key one for us was that it was one of the only ones that we could put in privately. And we looked at going to a Teleco supported platform, but unfortunately the costs were high. And I've actually got some reference slides a little bit later in the presentation, which anybody's welcome to have a look at, which sort of details some of those prices. And we effectively, the decision was, do we use a public versus a private network? And the big wins were in heading to a private network. You know, in summary, the third-party providers just didn't provide what we want. They were significantly more expensive. We didn't have to worry about a web portal into account maintenance. We didn't have any usage restrictions, which limited our data volume. We didn't have to wait for gateway deployments and those sorts of things where we didn't have coverage. We could just put them in. We had some concerns about public channels getting congested, and certainly over the next few years that could happen. So we actually changed to another channel plan. New Zealand uses AS 923 as a channel plan. We decided to go to AU 915. It's the Australian channel plan. And the advantage of that was that we were away from the New Zealand public channel, but we also had access to Australian hardware. And most of the Australian equipment is based on AU 915 channel plan. It also enabled us to provide our own resilience because we could put in multiple gateways to overlap, and certainly we can then put in at least 3 gateways and have the gateways triangulate device locations, and they can do that to within a few meters. And then we were able to keep connectivity when we needed it most. So in storms and those sorts of events, we've experienced where teleco interfaces failed, and in some cases, in 2018, we lost internet connectivity for 4 hours. Well, if you're trying to find out what's going on to your network, it's probably not the ideal. And certainly the other thing too is that we weren't vulnerable to third-party pricing and fluctuations. So it gave us some control about OPEX. And then from there, we developed a whole bunch of project streams, and we knew we needed gateways. We knew we needed some sort of server to be able to capture the data. From our use cases and meetings, we worked out that fault path indicator was something we wanted. It connects to a ring main unit, allows us to detect whether a fault has passed that particular point. We wanted to look at power quality sensing, and that was really for analysis and fault identification. We want to drop out fuse sensors. We have one particular fuse element that's failed 17 times in the last 18 months, so we were keen to look at DDO fuse sensing. We also wanted to look at voltage presence, and we've got a 3-phase version we wanted to look at, and a single-phase version we wanted to look at. We wanted to also look at EV charger control and DER, and yeah, it's a large list and it's quite comprehensive, and we thought, well, we needed to start somewhere. So we got into gateways, and we decided to start looking at what we would need to do with gateways. So we talked to our contractor, and we went through a process of using some RF propagation software, and we mapped what the RF propagation was from our substations and repeater sites. And the reason we used those was because they already had comms and internet already at those locations, or it was planned. And that enabled us to select about 15 sites. And the first site was installed at head office, and we've got one in Palmerston North for development, and we've actually got 12 gateways installed at present. And at the moment, each node sees 3 gateways, and that allows a bit of redundancy and resilience, and also gives us triangulation without having to actually have GPS. The gateways have GPS installed in them, and that allows us to synchronise timing and get those. And as I say, gateways cost about 1,800 plus an aerial plus installation. We found that height works best, so putting it on a hill. Mounting on buildings is not ideal. Certainly the metal inside buildings seems to cause further problems. Cell towers swamp signals. Aerial plants help, but best to keep those cell phone towers at a distance. Tin buildings, garages and those sorts of things, and wire fences block signals. And certainly we discovered that we started off with this channel plan, AS923, which is 923 megahertz, around about that range. But we found sourcing gateways and especially nodes to be very, very difficult because AS923 is not a common channel plan, whereas we could get AU 915 stuff, which is the Australian channel plan, very easily. And we did a little bit of a study into it, and we found that the AS 923 only had 16 channels, whereas AU had 64. And on the AU channel plan, we could have a little bit more power, and that gave us a 1.6 times range extension. And currently we've got a sensor in Tokomaru talking to head office in Laverne, and that's about a 40k range. So we're quite impressed with that. So yeah, so we've put in a few gateways, got a few more to go, and we're just about finished on the gateway front. We've got a Res IoT server, and the reason we chose Res IoT server was that it was free, the first one, and then you could then move to an open license, which was pay as you go. And we've just started to breach the point where that license is starting to get over the point where it's cheaper to look at an on-premise license. And an on-premise license is about €1,900, but it gives us support for 16 gateways and 544 nodes. And at the moment, we've got 12 gateways and around about 120 nodes. We needed 2 instances of that too, by the way, one on standby, one running. So that added to the licensing cost. And certainly one of the key things we discovered was that the open model requires continuous connection to a licensing server in the States. And when we lost connectivity to the internet, the whole system fell over, and we lost data for about 4 hours. So going to an on-premise license would certainly remove that failure risk. So we were keen to head there. And then we then discovered we built a fault path indicator, and we built 25 of them. There was actually quite a little bit of development time in that, and it was really about coding and building boards, but it's effectively a very simple tool. It's just a digital input device. It's got 4 inputs. Whenever a state change occurs, it sends us a signal. And we put it into a Sigma F+C fault passage indicator, and whereas that would normally trigger a strobe, it now also triggers our FPI indicator, which sends us an alert. And that alert comes up in SCADA, and that allows us to act on it. Final BOM for that was about $250, so not expensive. We needed to look at antenna placement. Certainly didn't want them breaking aerials and those sorts of things. And we've also discovered that we can use it for other things, so generator starting, access control, and those sorts of things. So we actually decided to rename it and just call it a fault sensor. And this was the device that I said before. It only costs us 0.8 cents a month to operate. It only sends one message a day. It costs us 10 cents a year to run. We then moved on and developed a power quality sensor. This was actually quite an expensive exercise, but the actual devices themselves were quite costly. We needed to do a little bit of research on how to talk to them. We did a study and went through quite a lot of meters. We actually reviewed 10 different meter types, and the Acuvum 2 came out as being one of the best. It does waveform capture and those sorts of things. So we connected it to a LoRa C terminal. We built two variants, a pole and a ground mount, and effectively the server polls the PQ meter and it spits back 38 parameters, and it does that every 10 minutes. And we push all that data into a data cloud, an Azure data cloud, and we use Splunk to review that data. And if you can see the little picture, the little map at the bottom there, where is it? This one here is showing locations of power quality meters. And when you click on one, you can see some information, and that's power, relative power. I think that one is a bit small. What we discovered, BOM price about $2,300, which is not cheap, but 2,000 of that is effectively the meter. Doesn't take long to install, it's only an hour. It takes 4 Modbus packets to actually do a read of data, and that takes about 20 seconds. So if you do the sums, we can only fit about 30 meters and 30 requests into a 10-minute period, and currently we are reading every 10 minutes. So we've got 25 meters installed, so we're right at the limit. So we need to look at whether we need to slow that reading down or whether we need to change our technology. And one of the other things we identified was that we really should have added temperature sensing to that power quality as well. And certainly we've got another 35 PQ meters planned for this year, so I need to work out what the solution is for that fairly soon. But certainly as a LoRaWAN device, it costs us 43 cents a month or thereabouts to communicate. So quite economic. And then we looked at a dropout fuse sensor, and this was offered to us by PowerCo. PowerCo developed this with a company in Australia, and it basically uses a tilt sensor to determine that. It has a lot of features, this device. It's got GPS in it, it's got a USB terminal interface, it's got a lot of things, and it's very complex. A little bit difficult to set up, and certainly the early ones had no mounting bracket, and they're a little bit difficult to mount. We ended up mounting with a couple of cable ties that are rubber silicone sealer for a window, and it seemed to work very well. But unfortunately, we found them to be a little bit fragile. Installation requires an outage because it's on a DDO fuse. We found the battery life to be a little bit poor. In fact, I've had units go flat already, and we've only had them 6 months. So it could best be a case of this particular prototype, but it certainly prompted us to look at alternatives. And what we looked at was to develop a solar variant, and that's this one down here. And we've managed to, it suits what we wanted to do, and it certainly costs a lot less. And one of the key features at 30 minutes in the sun, and it operates for 10 days. So that sort of eliminates us having to really leap in there and start swapping batteries out.
We've got 4 minutes to run, Darren, just for your information.
Yeah, sorry, I'll try to go quick. We looked at outage sensors, and we discovered that poor signal strength, they didn't really work quite the way we were wanting. So we decided that a night light wasn't the best option for an outage sensor. So we decided to build a different version without the night light that's actually mounted in a pillar box. Certainly we've also looked at a low-cost voltage presence sensor, and that's more of a 3-phase device, and that's looking for pole mount. So we've got a single-phase one for homes and a 3-phase one for pole mount. We looked at electric vehicle charging controlling, electric vehicle charge controlling, and certainly domestic controlling was a little bit difficult. We built a unit. We found that you couldn't actually switch off AC mains. It wasn't WorkSafe compliant. And customer engagement costs were high. We really didn't get the benefit of electric vehicle charging controlling that we were hoping for. It certainly became difficult to do domestically. However, commercially, a lot more fun. we got into using this open charge point protocol, and it allows you to set high and low current charge profiles, and you can use that OCCP command to switch between the two. And we're actually using that at Electra. We've got 3 sites set up and it's working well. And certainly down here, we've got load control and time of use management. And then we got a little bit into distributed energy resources, and we tried inverters, we tried to control battery systems. We found that it's very, very difficult. So we actually thought, well, okay, we'll install a PV and battery system at head office so as we could experiment. And our learnings were really that the repayment period just didn't stack up financially. There was no standard inverter interface, so very difficult to actually interface with. But the learnings were we categorised our DER categories. We also learned a lot about what not to do. But what we're really keen to take from this is that we're going to start testing nano coatings and energy arbitrage once those markets are ready to go. All right. And then at the end of all of that, we developed a forum, and I just wanted to mention that PowerCo assisted us greatly in our IoT journey. And yeah, the benefits were some operational experience. We got some implementation experience, and then our learnings were that we are really committed to building a smart network. We can't do it alone. We certainly need the support of the industry. You need to partner with providers. LoRaWAN is good, but you need to keep the data low. We found that event-driven certainly is more efficient than polling. And then certainly storing and viewing data was just as complex as making anything else. And certainly it's enabled us to see a lot more of our LV network, and we've also discovered that DER and EV profile control is not suited to LoRaWAN. And then what we're going to do next is a little bit more of the same. It's enabled us to develop a DER strategy and a smart grid strategy. So we're moving forward, and that's me. I hope I managed to fit into the time.
You're right on the knocker there, Darren. Now, there are a heap of quick questions have come through while you were talking, Darren. I've got time for just one quick one from Tahira. How does the company join the NZEN IoT forum? Any suggestions?
You can email me, and I'm more than happy to give you contact details. I'll flip back to that page. There's my email down the bottom there. Certainly, if they want to email me, I'll forward them any details.
Thank you very, very much, Darren. Really exciting journey you've been through there. And there have been other questions, and I'm sure you'll be able to respond to those in due course. Now, we'd better move along because we're now to the final presentation from our webinar this afternoon. That went quick, didn't it? So our final presenter is Dr. Baba Das, and the title of his presentation is Advanced Analytics for Transformer Asset Management. Dr. Das works for the Middle East and Africa hub of the transformer business of Hitachi ABB Power Grids. He's based out of Singapore. He's responsible for ABB Power Grids' digitalisation push for digitally enabled transformers in the region. He graduated from the University of Canterbury, where he completed his PhD on harmonics mitigation in HV transformers using current reinjection. He was awarded the EEA Young Engineer of the Year award in 2017 for his work on design and development of the smart transformer. He's also a senior member of the IEEE. A new asset management platform called APM Edge, based upon the Reliability Centered Maintenance or RCM methodology for fleet-wide assessment of power transformers, utilises the principle of fault tree analysis, and this is now available from ABB Power Grids transformers. And this presentation is going to present a case study for us on the utilisation of the expert system and the AMP edge on a 25 MVA transformer, which helped in DGA data quality identification, predicting future dissolved gas trends, predicting when the DGA abnormal levels would be reached, the time available before pre-failure values are reached, and identifying likely causes of failure. And finally, recommending required tests. So let's hand over now to Dr. Barbadas to deliver his presentation for us.
Thank you, Roger. I hope you can hear me well.
Yeah, very well, thank you.
Perfect. Good afternoon, everyone, and thank you, Roger. Thank you, Peter, Sean, for giving me this opportunity to talk about our advanced transformer asset management software, which we have developed. So the topic, the agenda of my presentation, I will give you a quick overview of what the T-Expert ecosystem is all about, our digital transformer ecosystem, and then I'll introduce what APM Edge is, where APM Edge sits on this ecosystem, and then I will do a deep dive on the offline DGA algorithm which we implemented in APM Edge and give you a case study on a 25 MVA transformers. So when we talk about the digital transformer ecosystem, we call it the T-Expert ecosystem. In that ecosystem, we have digitized and digitalized transformers. Transformers can be digital distribution transformers, dry distribution transformers, or we have the digital power transformers. And once you have digitized transformers using lots of different kinds of sensors, you basically are then able to do a fleet management. And then what we do with the data, we send the data to our digital enterprise APM or APM Edge, which we have designed and developed for transformer specific application. And once we have the data in APM Edge, it will run its algorithms, it will tell us what needs to be done. On top of that, we do a lot of engineering studies, testing, training, consultancy. So that's our whole ecosystem. And the value which we bring in APM Edge is basically what we have done is we have a lot of service experts. We have done more than 30,000 power transformer condition assessment. And the software is basically like the knowledge, the domain knowledge which all our service experts had is now incorporated, or I would say it is now coded in the software. So we saw some particular kind of fault in a transformer, say in Africa, in US, all of that knowledge is now part of this APM Edge software. Why we have developed it? The reason is we now want to move from time-based to RCM-based maintenance. We used to do everything based on time. We used to do our maintenance actions based on time. And sometimes even if they were not needed, we still used to do it. Then we moved to condition-based maintenance where we planned the maintenance of the device according to the measured health or condition of, say, the transformer. In that case, criticality and the impact of failure of the transformer was not considered. Now we are shifting to reliability-centered maintenance where we account for the component criticality, the transformer criticality, and we develop the maintenance strategy based on how critical is the transformer to your network, what is the health, and what is the impact of failure of the transformer to the network. And then we prioritize our maintenance. So when I talk about APM Edge, we start add the nameplate data. If you have the heat run test data, we take that into account. We require data for bushing, for tap changers, DGA results, standard oil test results, inspections. Sometimes when you do transformer inspections, you have data which is not quantified. Oil leaks, paint flaking, dirt on the bushing. So all of that can now be part of APM-Edge. So what we have done is we have quantified attribute data and made it discrete. So basically there are two data types where you have hard solid numbers. Suppose you do the DGA test, you get X ppm. But when you go for a visual inspection, you will just write down good or bad, yes or no. That data can now be part of this APM-Edge platform, and we have discretized that based on our service experts. And once we have the data, we do a lot of analysis. We use standard oil test analysis, DGA analysis. If you have the CTs, if you have the top oil temperature, we can calculate what is the thermal aging of the paper. Depending on the bushing information, we do bushing analysis. We can do particle count, PD, tap changer analysis, cooling system, Furan. And then we use all of these algorithms to calculate what is the risk of failure of the transformer. And depending on the data, depending on the analysis, we calculate what is the remaining useful life of the transformer. And then we are also able to calculate what is the replacement score or the maintenance score based on n number of transformers which we upload to APM-Edge. And accordingly, we can calculate whether we should put focus on replacing the transformer or doing some sort of maintenance. Moving on, as I mentioned before, APM-Edge will take not only test results, inspection data, historical data, nameplate data. We also take into account if you have online sensor data, such as online DGA, online PD, moisture monitoring, all of that can be now fed into this APM-Edge advanced analytical software. And then we run a lot of different kinds of algorithms, and we try and calculate what is the risk matrix and what is the risk trend, and we give you a score on whether the transformer is either in the green zone or in the medium risk zone or in the red zone. Depending on that, we also calculate whether we should be replacing this transformer or we should be doing maintenance activity on this transformer. As I mentioned before, we do a very nice fleet analysis, and on that each transformer we do DGA analysis, both offline data and online data. We have the thermal model, standard oil test, bushings, tap changers. We use all of that data to calculate the probability of failure and what is the risk associated by operating that transformer at that particular condition. And then all the domain knowledge of our service experts, which we have incorporated in APM-Edge, we use the expert system, which is basically like the knowledge which our service engineers had, which has now been coded into this software. And it will tell you for DGA what kind of test needs to be done, when the test needs to be done, is there data corruption. I mean, all of that is now part of this APM-Edge software. And I will give you a case study on focusing on the DGA. When we talk about DGA, what we have done here is we have taken into account both online DGA and offline DGA. For offline DGA, we do both gas level and gas trend analysis. And we also take into account what is the accuracy of the lab. And then we calculate if the lab and the online DGA device is differing by X amount, the expert system will automatically tell you that the two are not matching. And in terms of online DGA, we have developed algorithms for lots of different online DGA devices, be it the Callisto 1, Callisto 9, our own CoreSense and M10, Hydran, because all the DGA online DGA devices are different. Every DGA device is measuring different gases. Unless you install a 9-gas DGA device, there is differences in what it is measuring. And based on that data, we have developed algorithms to make sure that if you have a Callisto 5, we do the analysis based on the data which we receive from Callisto 5. If you have the Callisto 9, we take all the 9 gases and do our analysis. So what is the output? Output is basically the calculations, which are calculations will give you some values which are performed as part of the analysis. And then the expert system will indicate what kind of problems have been identified by the expert system. And then finally, in terms of messages, we will give you textual findings on what has textual findings on the analysis, and we will also do some sort of diagnosis of the causes, and we try and give recommendations. Now, in this case study, we investigated a 25 MVA transformer. We got the oil test lab results, and then the test report, what the test report told the end user was that there is some problem which requires further action. Gases are low, DGA ratios are showing a fault temperature of less than 300 degrees, results are marginal, and they basically recommended please resample in 6 months' time. So once you get that test report, we do not know what is the risk of operating that transformer. We do not know what has caused the issue. We do not know how much time we have before maintenance or what may be the reason. So what we did, we asked the end user to give us the data. Not only that data, we asked him to give us the DGA data for how many years it was available. So we got data from 2016, 17, 18, and 19. And then we uploaded this data to our APM Edge. And in that process, we also got what is the accuracy of each gas from each individual lab. And we uploaded all of this data to our APM Edge software. So in July 2019, as soon as we uploaded this data, our offline DGA recommendation straight away recommended that the last data point is a statistical outlier because it showed an increase of more than 447% from the previous level. And we also said that considering the lab accuracy, the gas is 50% over the typical IC range. And the expert system automatically recommended that statistical outliers are usually caused by either data corruption or the sampling procedure is wrong, the sample has contaminated. And the recommendation was to double check. Basically, the recommendation was please take a verification sample ASAP. The verification sample was taken in September, and it showed that the ethane gas levels have actually gone up considerably compared to 2016, 17, and 18. Then we used the new data set and we uploaded it to our software again. And in this case, in September 2019, our offline DGA recommendation basically said that the latest sample showed that it is confirming that it is above 50% of the typical IEC gas concentrations. And we automatically did a linear interpretation, a straight line fit of the full 5 data sample sets. And it showed that ethane is going up at 60 ppm per year. And if this trend is continued, our statistical tools which we have implemented indicated that ethane will cross 100% above the IEC typical gas limits in less than a month. So now we are able to predict in future on when the gas levels will be higher than 100% above what is the typical recommended by IEC. And what did the expert system tell us? The expert system told us that the gases which we are seeing in this transformer is based on hot metal gases. And the causes of this is basically either you have a unintentional core ground where or you may have other factors such as the insulation deterioration. Basically, there will be circulating currents in the core which will result in hotspot. And if you look to your right hand side, we calculated the risk associated with this transformer, and you will see that the risk of this transformer is in the green zone. That means the transformer can be operated. Because we saw rise in hot metal gases and there was the CO by CO2 ratio was stable, it was confirmed that the overheating was happening in the oil and there was no paper involved. And that is why the risk was in the green zone. So what we wanted to verify whether what we recommended that in less than 1 month time, the gas levels will exceed 100% above the typical IEC limits. And the way we did it is we installed a online DGA device to this particular transformer. And then we got the data from that online DGA device. The DGA device we installed in September, and by October, because of our statistical model, we saw that even the online DGA device showed that the gas levels have actually gone up by, actually crossed the 100% threshold above your normal DGA limit. So the expert system basically clearly indicated that ethane is coming from a localized heating source rather than an overall heating of the transformer. We calculated hot metal gases, what is the likely temperature, and we recommended what tests we need to do to figure out what has gone wrong. So just to summarize, so what we are doing now is we are basically checking the gas levels and the gas trends simultaneously. We check the gas levels against the IEC levels, IEEE, or even you can put in your own numbers. We also take into account what is the accuracy of either the sensor or the lab. And when we are breaching level 1, which is the typical IEC limit, if we see that the gases are going in such a rate that you will see that it will reach number 4 condition, we will immediately alert the asset manager, and we will warn if the gas levels are in level 2 and level 3. And when we are doing simultaneous gas trend analysis, we evaluate how long it will take for the gases to jump from either 1 to 2, 2 to 3, 3 to 4. And we have also implemented statistical modeling to detect accelerated trends. And we automatically calculate what is the ppm per year rate of rise. And if it is an online DGA device, we do 30-day short-term trends, and we do also do a 10-day very short-term trend. And as soon as we see some issue, our expert system will give you flags. It will, if we see that in less than a month the gas levels are going up, we will straight away send an alert message. If it is within 3 months, we'll warn, and if it is in 6 months' time, we will just give a prediction message. The whole idea is that within 1 month's time, we have less time to react, whereas in 6 months' time, we have more time to react. So the message change depending on how much time is available for the gases to jump from one level to another level. And finally, only when we breach either the gas level or the gas trend, we use Duvel triangle, Rogers ratio, IEC 60599. If and when we detect an issue. If both the gas levels and gas trends are within bounds, we do not use Duvel triangle or Rogers ratio, just to avoid false prediction or false. I mean, sometimes you do not need to use Duvel triangle because Duvel triangle will give you results every time. So that's how we have managed to cut out false warning message or false prediction message. That's all I had. Thank you.
Thank you very, very much for that, Baba. We appreciated your fine presentation there.
Thank you.
Now, I've only got one. No, I've got several questions, but only one for you, I'm sorry. So I'll ask you that now. Now, this is a question from Tahira. Hi, Baba. Is APM Edge and edge computing technology installed on a transformer, or does it work for customers who don't buy the enterprise APM? You have to unmute yourself again, Baba.
Yes, I have unmuted myself now.
Cool.
Yes. So yes, APM Edge is only for transformers. You do not have to have the enterprise APM, and it is installed in a Edge Edge PC. So it's basically once you have the sensors in the field, or even if you don't have any sensor on the field, you can manually upload. It's entirely up to you how you want to get the data. But if you have the Core Sense online DJ device, you can do direct data transfer from the sensor to the Edge PC, and then the algorithm will run on its own. Yeah.
Okay, thank you very, very much for that, Baba. Well, we have just a moment for, I had another question for Nutman here. Sorry if you're still with us. I missed out on before. This is from Frank. He said, good stuff. Have you verified your models with live installations?
So one of the slides that I shared during the presentation talk about cross-validation. So within ArcGIS itself, there's a basically you can perform geostatistical analysis within ArcGIS. So the way that it works is that it removes some known points from your dataset, and it tries and validate how closely matched it is to your predicted value. So I guess to answer your question, we have done some validation on the model, some using lab installation, some using sort of approximated values. What we see is that they can be plus minus up to 0.5 degrees Celsius meter per watts in terms of salt and moisture value, in terms of the error rate. So I guess that's essentially the answer to that question.
Thank you, Nutman. And one more from Dougal. What percentage of the network length is covered by the soil data samples?
So in terms of the sensor itself, we have about 93 installed on our network. So we've strategically located near feeder head, where we essentially see the highest loading on our cable. When we carry out the project, initially we were targeting mainly the high voltage or the 50 kV. We do install it at 11 kV, as I mentioned, at the feeder head. In terms of length, I'm not. I guess it's because it's a spot location, so it's actually sort of like on-site measurement rather than covering the entire length. So the idea is that because we want to limit or reduce the number of sensors we install, that's why we perform the soil digital twin. So we can reduce that number and do it through special interpolation technique to predict the soil measurement at unmeasured points or unknown points.
Thank you very, very much. Now, look, I'd like to especially thank our three presenters this afternoon for going to the trouble of preparing their presentations, for delivering them so well that the quality was excellent. On behalf of the EEA too, I'd like to thank so many for coming along to join. What an excellent way of getting world-class engineering advice, if you like, and thank you to Peter and Sean for arranging this. So I believe the next webinar is coming up around about the 25th of August, so don't feel shy in letting everyone else know about it. Let's get as many engineers and EDB participants, industry participants along to share in the fun, and I'm sure we'll look forward to that as well. So thank you very, very much, everybody. We've come to the end of our allotted time. I've really enjoyed this. Thanks for coming along, and I wish you all well, and hopefully the lockdown won't come back and we'll see each other in person again one day. Thank you, everyone.